Imagine standing in front of a machine so powerful it can push hundreds of tons of earth as if it were nothing more than a pile of sand. The ground shakes beneath your feet. The roar of diesel engines echoes across the landscape. Yet most people never stop to wonder how a bulldozer, one of the most important machines ever built, actually comes to life.
To build a bulldozer, manufacturers must gather materials from multiple continents, process them through some of the most advanced factories on Earth, and test every component under punishing conditions. We are about to follow that incredible journey from raw rock buried deep underground to a machine capable of reshaping entire landscapes. And what happens inside those factories surprised even experienced engineers. Every bulldozer begins with steel, and that steel begins as iron ore pulled from enormous open-pit mines. Some of the world's largest supplies come from Western Australia, Brazil's Carajás region, and mines across Canada. Massive haul trucks carrying more than 300 tons of, or crawl up steep mine roads day and night. Most people never think about it, but a bulldozer's first journey starts thousands of kilometers away from any factory. The iron ore often contains between 55 and 65% iron. Before manufacturers can use it, enormous processing plants crush, separate, and concentrate the material. Conveyor belts stretch for kilometers across rugged terrain. The air smells of dust and hot machinery while crushers thunder around the clock. Steelmakers then combine the concentrated ore with metallurgical coal, much of it sourced from Australia, the United States, and Mongolia. Inside towering blast furnaces, temperatures exceed 1,500 degrees Celsius, or 2,732 degrees Fahrenheit. Molten metal glows brighter than the sunlit sky outside. Rivers of liquid steel pour through the factory like man-made lava. A modern bulldozer can contain more than 70 tons of high-strength steel, depending on its size. Manufacturers carefully select different steel grades for different jobs. Some sections must resist crushing loads. Others must survive constant vibration, impacts, and years of punishment in harsh environments. And this is where the first hidden secret appears. Not all steel ends up in the bulldozer's frame. Some of the toughest steel becomes cutting edges and wear plates on the blade itself. These components endure relentless abrasion from rock, gravel, and compacted soil. In some mining operations, a blade can scrape against material harder than concrete for thousands of hours. Steel is only the beginning. Bulldozers also depend on copper mined in countries such as Chile, Peru, and the Democratic Republic of the Congo. Hidden inside wiring harnesses, sensors, control modules, and electric systems are hundreds of kilograms of conductive copper. Without it, the machine would be blind, deaf, and unable to communicate with its own systems. Photorealistic, cinematic, ultra-detailed, 8K, industrial documentary style, copper mine transitioning into bulldozer electrical systems, glowing copper wiring harnesses, sensors, and electronic modules integrated into heavy machinery, dramatic lighting, industrial atmosphere, orange and blue industrial color grading, wide-angle lens, depth of field. Photorealistic, cinematic, ultra-detailed, 8K, industrial documentary style, copper mine transitioning into bulldozer electrical systems, glowing copper wiring harnesses, sensors, and electronic modules integrated into heavy machinery, dramatic lighting, industrial atmosphere, orange and blue industrial color grading, wide-angle lens, depth of field. But here's something rarely discussed. Producing the raw materials for a single bulldozer can generate a significant carbon footprint before manufacturing even begins. Mining operations consume enormous amounts of energy. Steel production remains one of the world's largest industrial sources of emissions. Engineers now face a challenge that could redefine the future of heavy equipment. Because while the world's demand for bulldozers continues to grow, manufacturers must somehow build stronger machines with fewer environmental impacts. New alloys, recycled metals, and alternative production methods are already changing the industry. And waiting inside the factory is an engineering process so precise that a fraction of a millimeter can determine success or failure. That's where our journey goes next. The moment raw materials arrive at the factory, the transformation begins. Towering steel plates weighing several tons each move through the facility on automated carriers. Every piece carries a digital identity that tracks its journey from the mine to the finished machine. Imagine standing beside a sheet of steel larger than a small house, knowing it will soon become part of a bulldozer capable of moving mountains. The first major step is precision cutting. Computer-controlled plasma cutters blast through thick steel using superheated ionized gas reaching temperatures above 20,000 degrees Celsius, or more than 36,000 degrees Fahrenheit. Brilliant white sparks explode across the factory floor while robotic arms guide the cutting heads with millimeter accuracy. The air smells faintly metallic, and the sound resembles a continuous thunderstorm trapped inside a building. Next comes forming. Massive hydraulic press brakes apply forces exceeding 1,000 tons to bend steel into precise shapes. Some components require multiple bends performed in exact sequence. A deviation smaller than a few millimeters can create alignment problems later in assembly. Most people never think about it, but every curve and angle in a bulldozer frame begins here. Then the factory reaches one of its most dramatic stages: welding. Skilled welders and robotic systems join giant structural components together using electric arcs hotter than 6,000 degrees Celsius, or nearly 11,000 degrees Fahrenheit. Molten metal flows along seams like glowing liquid fire. What happens next surprised even experienced engineers, because some bulldozer frames require hundreds of meters of welding before they become a single structure. After welding, engineers inspect every critical joint. Ultrasonic scanners send sound waves through the metal to detect hidden flaws invisible to the human eye. Even microscopic cracks can grow under years of heavy loads. The factory refuses to take chances because a bulldozer may spend decades operating in some of the harshest environments on Earth. While the frame takes shape, another team builds the heart of the machine: the engine. Massive diesel engine blocks arrive from specialized foundries where molten iron was cast into molds weighing several tons. CNC machining centers then remove tiny amounts of material with astonishing precision. Some surfaces must stay within tolerances thinner than a human hair. While the frame takes shape, another team builds the heart of the machine: the engine. Massive diesel engine blocks arrive from specialized foundries where molten iron was cast into molds weighing several tons. CNC machining centers then remove tiny amounts of material with astonishing precision. Some surfaces must stay within tolerances thinner than a human hair. Inside those machining centers, cutting tools spin at speeds exceeding 5,000 revolutions per minute. Streams of coolant spray continuously across the metal to control heat and protect tool life. The smell of machine oil fills the air while polished surfaces emerge with mirror-like perfection. Every measurement undergoes repeated verification before the part can move forward. While the frame takes shape, another team builds the heart of the machine: the engine. Massive diesel engine blocks arrive from specialized foundries where molten iron was cast into molds weighing several tons. CNC machining centers then remove tiny amounts of material with astonishing precision. Some surfaces must stay within tolerances thinner than a human hair. The transmission follows. Engineers assemble gears, shafts, bearings, and clutch systems designed to handle enormous torque. Some gear teeth undergo heat treatment in furnaces operating between 850 and 950 degrees Celsius, or 1,562 to 1,742 degrees Fahrenheit. The process changes the internal structure of the steel, creating extraordinary hardness while preserving toughness deep inside. The transmission follows. Engineers assemble gears, shafts, bearings, and clutch systems designed to handle enormous torque. Some gear teeth undergo heat treatment in furnaces operating between 850 and 950 degrees Celsius, or 1,562 to 1,742 degrees Fahrenheit. The process changes the internal structure of the steel, creating extraordinary hardness while preserving toughness deep inside. Before painting, the entire structure passes through cleaning and preparation systems. High-pressure washing removes contaminants. Surface treatments improve corrosion resistance. Some facilities use automated blasting systems that propel abrasive particles at high speed to create the perfect coating surface. The machine emerges cleaner than a surgical instrument. The paint shop feels almost futuristic. Robotic spray systems apply multiple protective layers under carefully controlled conditions. Temperature, humidity, and airflow remain constantly monitored. Bright clouds of paint surround the machine as its familiar industrial colors finally appear. For the first time, it begins to resemble the bulldozer you recognize. Finally, workers install the blade, cab, electronics, safety systems, and finishing details. Touchscreens illuminate. Sensors wake up. Diagnostic software checks thousands of signals in seconds. The machine that began as raw or buried underground now stands ready to move earth, rock, and entire landscapes. But here's the real mystery. Building a bulldozer is not enough. Manufacturers must prove it can survive years of punishment, brutal impacts, extreme temperatures, and relentless workloads. The next stage pushes these machines far beyond anything most owners will ever experience. And some tests are so extreme they look almost impossible. Photorealistic, cinematic, ultra-detailed, 8K, industrial documentary style, completed bulldozer positioned before massive testing facility doors, engineers studying durability test schedules, dramatic lighting, light steam and industrial haze, orange and blue industrial color grading, wide-angle lens, depth of field, suspenseful documentary atmosphere. The first inspection often begins with laser scanning systems. High-speed lasers sweep across the bulldozer, capturing millions of measurement points in just minutes. Powerful software compares every surface against the original digital design. Some critical dimensions must stay within tolerances as small as 0.2 millimeters. Most people never realize that a machine weighing more than 100 tons can require accuracy measured in fractions of a millimeter. Then AI-powered vision systems take over. Arrays of ultra-high-resolution cameras inspect welds, paint surfaces, hydraulic connections, and electrical assemblies. Artificial intelligence compares every image against thousands of known examples. A defect invisible to the human eye can trigger an immediate alert. What happens next surprised even experienced engineers, because the system can identify flaws in seconds that once required hours of manual inspection. The hydraulic system faces its own challenge. Engineers pressurize the entire network to levels exceeding normal operating conditions, often surpassing 350 bar, or more than 5,000 psi. Sensors monitor every connection for leaks, pressure drops, and abnormal behavior. Even the smallest weakness can lead to rejection. In some factories, fewer than 1% of hydraulic systems fail these tests, but every failure receives a complete investigation. Next comes engine testing. The machine moves onto a dynamometer where engineers simulate real-world workloads without leaving the factory. The engine roars under controlled conditions while computers measure power output, fuel efficiency, emissions, and cooling performance. Heat radiates from the machinery. The smell of diesel fills the air. Every vibration tells a story about the machine's health. But the factory is not finished. Some components enter specialized fatigue testing laboratories where hydraulic actuators repeatedly apply enormous forces. Certain tests run continuously for weeks or even months. Millions of load cycles simulate years of operation in mines, quarries, and construction sites. Engineers deliberately push parts toward failure because understanding weakness is the key to building strength. The undercarriage receives some of the harshest treatment. Track assemblies endure simulated impacts, abrasive wear tests, and extreme load conditions. Massive machines grind, compress, and stress components around the clock. Most people never think about this, but a bulldozer's tracks may travel across thousands of kilometers of rock, mud, gravel, and frozen ground during their working life. Environmental chambers create conditions that feel almost impossible. Engineers expose components to temperatures below -40 degrees Celsius, or -40 degrees Fahrenheit, then test them again at temperatures above 50 degrees Celsius, or 122 degrees Fahrenheit. Moisture, dust, vibration, and corrosion accelerate years of weather exposure into a matter of weeks. The goal is simple: find every possible weakness before customers do. Before painting, the entire structure passes through cleaning and preparation systems. High-pressure washing removes contaminants. Surface treatments improve corrosion resistance. Some facilities use automated blasting systems that propel abrasive particles at high speed to create the perfect coating surface. The machine emerges cleaner than a surgical instrument. International certifications add another layer of scrutiny. Manufacturers must comply with standards covering safety, emissions, quality management, and environmental performance. Every document, measurement, and procedure undergoes verification. Behind every bulldozer stands a mountain of engineering records proving the machine meets strict global requirements. Yet even in an age of automation, there is one moment when human skill still beats machines. Veteran inspectors walk around completed bulldozers listening, touching, and observing details that software sometimes misses. A slight vibration, an unusual sound, a subtle movement. Decades of experience allow them to notice patterns that no algorithm fully understands. And this is where manufacturing becomes part science and part art. Only after passing hundreds of inspections does the machine reach its final proving ground. Test operators drive the bulldozer across steep slopes, rough terrain, mud pits, and obstacle courses designed to expose hidden problems. The blade bites into the earth. The engine growls under load. Every system must work together flawlessly. For the first time, the machine experiences the job it was built to perform. And this is where it gets truly extraordinary. After thousands of components, countless inspections, and months of manufacturing effort, the bulldozer finally earns approval for delivery. But the story does not end at the factory gates. Around the world, these machines drive industries worth hundreds of billions of dollars, shape entire cities, support mining operations, and help build the modern world itself. The numbers behind that global impact are almost impossible to imagine. Now let's zoom out and look at the bigger picture. Every year, manufacturers around the world produce tens of thousands of bulldozers, ranging from compact construction models to giant mining machines weighing more than 100 tons. Together, the global earth-moving equipment industry generates well over $100 billion annually. Imagine every skyscraper, highway, airport, mine, and dam built over the last century. Somewhere near the beginning of that story, a bulldozer was usually involved. The largest share of bulldozer manufacturing comes from China, followed by the United States, Japan, India, and Germany. Together, these countries account for the majority of global production. Massive factories operate around the clock, producing machines destined for projects on nearly every continent. Most people never think about this, but a bulldozer working in Africa or South America may contain components sourced from more than a dozen different countries. Finally, workers install the blade, cab, electronics, safety systems, and finishing details. Touchscreens illuminate. Sensors wake up. Diagnostic software checks thousands of signals in seconds. The machine that began as raw or buried underground now stands ready to move earth, rock, and entire landscapes. Think about the workforce behind these machines. Hundreds of thousands of people contribute directly or indirectly to bulldozer production. Miners extract raw materials. Metallurgists develop advanced alloys. Engineers design components. Factory workers assemble systems. Logistics teams move materials across oceans. Every bulldozer represents the combined effort of an enormous global network of expertise. The history of the bulldozer stretches back more than a century. Early versions appeared in the 1920s when engineers mounted blades onto agricultural tractors. Those pioneering machines looked simple compared to today's giants. Yet they transformed construction forever by allowing workers to move earth faster than ever before. What started as a practical invention eventually became one of humanity's most important tools. Over the last 50 years, bulldozers have changed dramatically. Engines became more powerful and fuel-efficient. Hydraulic systems gained precision. GPS guidance transformed job site accuracy. Modern operators can move enormous volumes of material while following digital terrain maps displayed inside climate-controlled cabins. The difference between an early bulldozer and a modern machine is like comparing a propeller airplane to a jetliner. Did you know that some mining bulldozers use blades wider than a city bus? Standing beside one feels less like approaching a vehicle and more like standing next to a moving building. The scale becomes almost impossible to comprehend until you see a person standing nearby. Suddenly, the machine looks absolutely gigantic. Did you know that a single large bulldozer can move thousands of cubic meters of material in one day? That is enough earth to fill dozens of backyard swimming pools before sunset. The machine never gets tired, never slows down, and never complains. It simply keeps pushing forward hour after hour. And perhaps the most extraordinary part is that this process happens again and again, thousands of times every year, driven by human creativity, engineering skill, and relentless innovation. Behind every bulldozer stands an invisible army of workers, engineers, scientists, technicians, and operators whose efforts make modern civilization possible. They never hear the thunder of blast furnaces, the crackle of welding arcs, the roar of test engines, or the precision hum of CNC machines shaping steel to microscopic tolerances. Yet every one of those moments helped transform raw materials into a machine powerful enough to reshape the earth itself. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.